So my name is Akash and I'm from CDAC Pune. So in the morning, we have started with the introduction to the GPU programming. So I hope you got a good idea about how GPU looks like and what is the architecture of it and how the CUDA programs work, right? So now we are moving to the hands-on session. So in this session, whatever that we are going to cover, I'll just give you a brief idea about that. So right now, you don't have any access of supercomputer right now. So we are using open source platform Kaggle. So we will create an account on Kaggle. Then we will see how CUDA program execution flow looks like. Then we'll see a basic Hello World program in CUDA. Then we will move on the device information program in CUDA. Then we'll see vector addition, how we can do it using the CUDA. And then at the end, we will see how we can do the matrix multiplication, both the serial and the parallel programs in CUDA. So by using the matrix multiplication, you can understand how the performance will be improved by using the CUDA, right? So before that, I'll just share you one screen. So you have to create, first of all, the account on Kaggle. So I'll just show you the steps, how you can create. Parallelly, you can do, right? So first, go in any browser and type Kaggle. Do parallelly with me, right? Okay. Then click on the link. Then right now you can able to see this interface. Are you all here? Right? In this page? Okay. So in the top right hand corner, you can see the sign in and register option. So if anybody from you having the account on Kaggle, you just need to sign in. And if you don't have any account on Kaggle, just register with your email. I hope that you are doing this, right? You can just simply click on your Gmail and your account will be created automatically. So have you registered? And just confirm. Okay. So now you can see this kind of screen. Am I right? Welcome, then your name. Then in the left hand corner here, go to home. So I hope that you can able to see this screen, right? Then go into the top right corner here. Click on that. Then you can see the settings bar. Click on that. Then, so here, phone verification. So here, mine is verified. So if you are a newcomer on Kaggle, So your mobile number is not verified, right? So you have to add here your mobile number. Then you will get an OTP. Just to verify that. Because we have to use the GPUs. So Kaggle by default just give the support for the CPU. But if you want to use the GPU, you have to verify the phone number. It will take a few seconds to get OTP. Just verify that. I hope that you are following this process. Once it is verified, then please let me know. If somebody has already verified, then don't follow this process. So have you all reached here? Can anyone just confirm? So shall we move ahead? Okay. Then just click on the plus sign here, create, then notebook. So here you can see the Jupyter notebook-like interface.
Hello. For those who have international numbers, I hope the verification process has worked. Nope. So one possible way you could try is maybe take somebody's else's number and try it. I don't know whether that will work. Yeah, but that's a quick and dirty hack. I think we can try. Oh yeah, so Harsha has a spare number if somebody. Yeah. The international participation.
Okay. Right. So shall we move ahead? I think you had a Linux session before it, right? Linux Singularity and. So how many of you have the familiarity with the Linux commands? Okay. That's not an issue. I'll just give you a brief idea about that. So can anybody just confirm? Are all set? Right? Fine. Then here you can see the console of Kaggle. Then just scan this QR by using the Google image. You can get my Google repo link. So after scanning this, you will be redirected on my GitHub repo, where I have placed the CUDA codes. Yeah. Yes. Okay, fine. Okay, this is the URL. So just type this QRL or in the Kaggle console. So here I have copied it. Go to the Kaggle. So here, if we want to use the Linux commands on the Kaggle notebook, we must specify exclamatory mark first. So first of all, we have to copy the codes from the Git repo to our Kaggle notebook. So just type the command git clone, then this URL. And just press Shift Enter. It is a web-based portal, so it will take a little bit time. Then exclamatory mark ls. By using this command, you can see whether the folder is copied here or not. So here I can see ICTS GPU programming folder. Okay. Then just copy one command, cp-r ICTS GPU programming /* dot. So what this command does, it will copy the content of that ICTS GPU programming folder in the current location.
Has everybody cloned the GitHub repository? Has everybody found the GitHub repository? Okay, so I think we have shared the link on Slack in the workspace for the conference workspace. So do have a look, get the link from there, get the repository cloned, and then we can go ahead from there. still finding the link to the GitHub.
Okay, fine.
Hello. Excuse me. So in the Kaggle, which how to work with the Jupyter notebook? Plus create and then create हो गया.
I'll again repeat the process for the Kaggle account creation. So are you able to copy this GitHub repo? So shall we move ahead? Or still some people are remaining? Can anybody just confirm? Shall we move ahead? Yes, okay, fine. So I hope that you reached here. You have cloned the repo. Then you just wrote this command. Just shift enter. Now I'm doing ls, list of the files. So here you can see there are 5 codes present over here. Hello world, vector addition, device information, matrix multiplication. Okay. So before moving forward, we just look how actually the CUDA program flow looks like. So see, so the first step, whenever we start writing program in CUDA, we must have to specify the memory allocation, right? So here, the first step is to host, that is CPU memory allocation and data initialization. So whenever you start programming in CUDA, so basically the GPU is an accelerator. It is a different hardware which is attached to the CPU, right? Suppose, here is an example. Suppose you have a CPU that is a multi-core device and this is its memory, system memory. And the right hand side, you can see the GPU, right? Having thousands of the cores with its GPU memory, right? So first thing, you have to initialize the variables that you want to perform operations on that. You have to initialize it in the system memory, that is in the CPU's memory, right? So this is the first step, and how you can do that by using the malloc function, memory allocation, that is dynamic memory allocation function in C language, right? Then after, in the second step, you allocate the memory on GPU device. So first you have done with the CPU, then you have to move to the GPU. You have to allocate the memory on the GPU as well for the same variables, right? This is the second step. Then third step is to transfer that data from host to device memory. So basically these two terminologies always comes in the CUDA, host and the device. Host means the CPU and the device means the GPU. So the third step is to transfer that data from host to device memory. So here we have initialized the memory for the variables. Then we are going to transfer that memory to the, we are going to transfer that variables from CPU to the GPU. Okay. That is the third step. Then whatever the task that we have to perform, whatever the operations that we are going to perform, that we write in the kernel function. Okay. So the kernel is the main execution part of any CUDA program. So we can call it as a kernel. So the actual execution that we are going to do is on GPU. So we are transferring that kernel from CPU to GPU. So GPU computes all the tasks and all, whatever that we have defined, and then again, it will send back the results to the CPU. So that is the basic actual flow for the CUDA program execution. So see, data transfer from device to the host memory. So after completing the tasks on the GPU, it will send back that results to the host memory, that is on CPU memory. And after that, after finishing all the tasks, you have to release the memory, because in future, if you want to do another operations and all, so for that you must have to free the memory. So this is the basic program execution flow for the CUDA. So I'll move on the Kaggle. So here, so right now we are on the CPU. So how we can see that? So in the top side, you can see the settings here. Okay. I hope that you can able to see. So here is the second option, that is accelerator. So here we have selected none. So if you have successfully registered with your mobile number, then you can able to see these three options: GPU T4 into 2, GPU P100, TPU. If you have not successfully verified your mobile number, then you can't see these options, right? So that's why I have initially told you to register the mobile number. So right now I am selecting here GPU T4 into 2. You can select any one of them. So right now I have got one top up. So there are some policies of the Kaggle that limited access for 30 hours per week. Turn on GPU T4. So it will take a slight time to start. You can cross verify from here that is it successfully started or not. So here you can see T4 into 2 GPU. So our session is moved on the GPU, right? So now if you see the content of our Kaggle notebook, so it will vanishes. Whatever that we have downloaded, because Kaggle provides a temporary setup. Whatever the command that I'm going to write down here, please copy it somewhere so that you can again able to perform these operations. So here I have run the ls and you can see nothing is there. So these folders are vanished. So just again clone this repo, shift enter. So here ICTS GPU programming is here. Then again copy the folders from that folder to the working directory. So now I'm here. So to check whether my GPU is working or all the drivers and the libraries are installed properly, so there is one command you can type. So first of all, I want to check the compiler whether it is installed properly or not. So the NVIDIA provides this compiler nvcc space hyphen hyphen version and then shift enter. So here, all the CUDA drivers and the packages that are successfully installed on this GPU T4, right? So if you can't see, if you see any error like this command is not found, so CUDA is not properly configured with the Kaggle. Then again there is one command, NVIDIA -SMI. So by using this command, you can see the utilization of the GPUs. So here you can see the information like this. So this is the NVIDIA SMI. This is the version number, driver version. Then the CUDA 12.6 we are going to use. And here we have a T4 into 2. When we have selected the accelerator, we have seen that T4 into 2. So there are 2 GPU cards are there. So these are the basic commands. Okay, let's move ahead. So let's see the basic Hello World program. Whenever we start to learn any programming language, first we write down the Hello World program. So here, I'll just see the content of this file. So this is the basic C program. So basically CUDA is an API which is built on C, C++ programming languages, and there are also some of the implementations in the Python as well. So this is a very basic program in CUDA. Later we will move ahead with some complex operations. So hash include stdio.h, that is the basic header file that we mention in the C file. Then here is the kernel. So what actually it is? So I'll just CUDA provides basically 3 function declarations for offloading the task from CPU to GPU. So basically, always we use the global first, right? So underscore underscore global, then underscore underscore, right? So this is the syntax for that. So what actually it does, it declares that kernel, okay, that is called on the host and executed on the device. As same I have mentioned. So first we will initialize the memory on the CPU, then we will transfer onto the GPU. So these work can be done by this underscore underscore global qualifier, right? So how we can write that? So whatever the task, whatever the function that you have to offload on the GPU, you can write this by using this syntax, underscore underscore global underscore underscore void my kernel and the task that you want to perform. Then second one is device. So device is basically what it does. It declares, like we declare the device function which is called and executed on the device itself. So global, what it does, it will copy the data from CPU, it will transfer to GPU, then GPU perform the task and again it will send back to the CPU, right? But device is only runs on the GPU. So when you call any global function, then in global itself, you can define the device, because global, what it does, it will first call from the host, then goes on the device on the GPU. Then on GPU, you can again call the device function and you can do the operations on the GPU. Then the third one is host. So if you want to do any operations on CPU, then you can use the host as a function, kernel function. So there is no intervention of the GPU in the host, right? So this is the basic syntax for that. So here, what the task we have to do? We have to do this operation that print hello world from GPU on the GPU hardware, right? So here I have defined one function, hello world from GPU. So I have specified it as a global. So what it does, this portion of the code is going to be executed on the GPU. Then this is the main function. So here main basically works on CPU. So first it will print hello world from CPU. Then here, this is the main portion. So here you have defined the kernel and you have called it here. So hello from GPU, and what actually it is the size of the threads. So in a single line, we have to print 10 threads, right? So we haven't mentioned here any dimensions and all. So we can mention it later in our vector addition and matrix multiplication program. So right now, I just want to use 10 threads, which prints hello world from GPU. Then at the end, we are using the CUDA device synchronize. So what actually it does, it ensures all the print statements from the GPU are executed. So it will wait till all the threads done their work, right? And then return 0. So this is the basic program in CUDA. Then how we can compile it and run it? Just see NVCC, that is a compiler name. Then what is the name of our file? That is helloworld.cu, then -o, then. So why we have mentioned here the file name and all? So first thing, the compiler name you have to mention. So whenever you run any program in, I hope that somebody you have already worked on the GCC compiler and all. So as same like here, NVCC, the compiler name, then the file name, CUDA file name, then -o is for to generate the executable with the name this. Okay, if you not mention this part, still it will generate the executable, but its name is a.out. That is the default name, right? But after a certain time, if you run any other programs, then the a.out rewrites, right? So for that, we are mentioning here executable name, then shift enter, compiled. So here you can see 01 hello world executable, right? So this is this .cu is a file and hello world is the executable of that. Then how to execute that? Just ! ./ and then name hello world, the executable name. So here you can see the output. So basically, the main function where we have written hello world from CPU is written over here. Then the kernel function launched, and what actually written in the kernel function, that is hello world from GPU. So 10 threads we have spawned here. So that's why it is coming 10 times, right? So are you able to execute this code on your Kaggle?
Yeah. Can everybody follow along? Is everybody able to execute the code?
Parallelly write down all the steps in any text file or anything else, because sometimes it will vanishes. So this is a very simple program in CUDA, right? So we'll move ahead. So in the first half session, Bharat sir told us that we have a axis and all 3 dimensions. Then we'll see that. These are some of the dimensions and the thread indexes that we can define in CUDA. But before that, just see its description. So here, griddim.x, which is basically used for the number of blocks in x direction within a grid. So in the earlier session that we have seen, there is a one grid, and in that grid we have a multiple blocks, right? So to know the number of blocks in x direction within a grid, we use this variable griddim.x. Then the same, the number of blocks in y direction within a grid, we use this grid dim.y. Then in the z direction, we use grid dim.z, right? Why it is actually important, I'll just give you idea about that. And the ID, if we want to calculate the ID of that block, suppose we will give them numbering as 0, 1, 2, 3, 4. Okay, so that IDs we can get via this variable block idx.y, block idx.z. So x, that is index of current block in x direction within a grid, then in the y direction, then in the z direction. Then block dim.x. So in the block, we have a multiple threads, right? So number of threads in x direction within a block, we can, for that we can use this block dim.x. So if we want to identify how many number of threads in the y direction within a block, then we can use this block dim.y. Then if you want to see the number of threads in z direction within a block, then we use block dim.z. Then we remain with the thread IDs. So how we can identify the thread IDs? So these are some variables like thread idx.x, that is index of T3, T4, T5, T7, T8. Likewise, you have a multiple threads. So how you can identify the correct ID of that thread? So for that, these variables are defined in the CUDA. So here is the formula to calculate the thread IDs, global thread IDs. Suppose you have a number of blocks. So here I have taken 3 number of blocks. So you can use thousands or hundreds of the blocks, right? So how you can identify which thread is located here? So for that, we have a formula in CUDA. So for the calculation of total number of threads, we have the formula grid dim into block dim. So what actually the grid dim? So here you can see number of blocks within a grid. So how many number of blocks are present over here, right? Within a grid. So we have 3 blocks over here. And the block dimension. What actually the block dimension is? So number of threads within a block. So how many number of threads present within, just yellow are the threads, 3 are the threads in this block, these 3 are the threads in this box, and in the third box we have 3 threads, right? Likewise. So when we do the multiplication of this 3 into 3, what actually the result is 9. So how many number of threads are there? 9 number of threads are present over here. Then we have always need to calculate the global ID of the thread in the CUDA. So the formula for the calculation of global ID of the thread, that is equal to block ID dot x into block dimension dot x plus thread IDX, right? So we should know about block IDX, then block dimension and thread IDX. Then we can actually able to find out the global ID. Suppose we consider the block, this first block, then this is the thread 1, thread 2, thread 3. So these are the local IDs for the block 1. Suppose we consider block 2, then it has 3 threads. So like T1, T2, T3. So these are the local IDs for that blocks. Okay. And in the third box, we have T1, T2, T3. So these are the local IDs for that boxes, right? Blocks. So in CUDA, we have to identify the global thread IDs. So for that, we have to use this formula, right? So here, the blocks arrangement and the thread arrangements are in 1D, one dimension. So here, the grid dim.x, the dimension of the grid, that is blocks present in the grid are 3 in the x direction, and the threads present in the block are also 3 in the y direction, right? So here is the calculation of this. Suppose we take first block, that is 0, 0, 0. Okay, this block we are going to take. Then how many number of threads? 3 are there. Okay, so we are going to take here thread IDs. So the first thread having T00, T100, then T200. Okay. Then how we can calculate this? The global thread ID by using this formula. Block IDX dot x into block dim plus thread ID. So here is the same formula we have used. So here block ID, what we have in the x direction, that is 0. Okay. Into block dimension. So what is the block dimension? 3. 3 threads we have in the block. So into 3 plus thread IDX in the x direction, that is 0. So it will become the 0. So global thread ID for the T000 is 0. Then again for T100, same thing. 0, that is block ID into block dimension plus thread ID. So here in the x direction we have 1. So 3 into 0, 0 plus 1, that is 1 is the global ID for the T100. Then T200, then the same formula we have applied, and 2 is the global ID for that. Then again, we have taken the second block. So here the same process has followed, and 1 into 3 plus 0, that is block. This is the block ID into the x direction, that is 1 we have taken over here. Then into the block dimension plus the ID of the thread, right? So it will become 3, 4, 5, 6. So whatever that I have mentioned, right? So threads, the local IDs are 0, 1. Because I hope that you have understood this formula, right?
The significance of having this blocks along this
X, Y, Z direction. Like, suppose there are multiple operations. If you consider the matrix multiplication operation, right? So the matrix is in the 2D form, or you can say you have thousands of the threads, right? But you have arranged in such a way that, like, using the blocks. But if you don't know the IDs, so there is no significance of using the threads, right? So for that, you should know about each and every thread ID to calculate the accurate calculation. If you want to perform, then you should know about this. Okay, so for that we use this formula. If you have any doubt, then please let me know. Later we will use this in our code, right? Then you can able to understand why actually we have used this. Let's see the second program. So here we have the second program, the device information. That is the generic program to see the specifications of the GPU. So here again, NVCC space, the device information.CUDA. Here. So here the mistake is we haven't mentioned exclamatory mark here. Here, I think it is not created. So here, right now, you can see the information about your GPU devices. Let's see what actually written in the code. I'll see the content of this code. See you. Okay, see. As include stdlib and stdio.h we have included. In the main function, we have initialized one variable named as device count, and this is the CUDA get device function. It will invoke the device count, right? So if the device count is double equal to 0, then you can see there is no device supporting CUDA. So here we have selected the CUDA device. So that is showing us the two T4 GPUs. So if we haven't selected that GPU part, then you can see there is no device support in CUDA, right? So here, device, then device 0. Then if the device increases count, then these are some of the functions to get the properties. So if it found the one device, then two device, likewise the IDs, right? So this is the common specifications if you want to see. Okay. So here you can see there are two devices supporting CUDA, T4, again the device 0 and device 1 having T4, and these are the specifications. How many global memory is there, then clocks, multiprocessor streaming, multiprocessors count, warp size and all. Okay. Let's move to the next one. So now we will see the actual CUDA implementation program, that is vector code. Shift enter. Okay. So this is the code for the vector addition. So vector is nothing but in dynamic arrays. Arrays are fixed size, but the vectors size changes at the runtime. So here the same hash include stdio.h we have used. So the size of the dynamic array we have taken 5120 multiplied by 1 lakh. So here, this is the actual kernel in the CUDA, right? So whatever that we have seen in the PPT slide, that calculation of thread IDs, global thread IDs, it will be important here, right? So consider this is a simple function. So I have defined here one function, add vectors. So these are entry points. So 3 variables I have taken, int a, b, c. So basically the c is the output, the resultant vector, and a and b are the input vectors. So we are going to add them. So now, when we go inside into the global function, so here int id I have defined. So whenever we spawn any thread, suppose if anyone from you had used any OpenMP code or anything, parallel programming code, I don't know. But in parallel programming, the program works parallelly. But how? Actually, that work is divided into the multiple threads, right? So here is same thing is happening. So CUDA has thousands of the cores we have seen. So how that thousands of the core can be utilized? So by using this formula, because whenever you do the parallel programming, so each operation, each task, you have to define and you have to distribute at the same level. Like thread 1 is doing operation on this data, thread 2 is doing this one. Like suppose if you have A of I and B of I, suppose the 0th index you have to run using the thread 0, right? So you can use that. Then thread 1 is going to perform the operation A of 1, B of 1, then A of 2, B of 2 is going to be run on thread 2 likewise, right? So each thread is going to be assigned with the unique data items, and then it will perform their operation. So for that, we have to always need to calculate the global thread ID. So here is the formula how we can calculate that global thread IDs. So here the boundary condition, the ID should be less than this defined n size, right? So if we take the element size 10, right? So what are the IDs of that threads? 0 to 9, right? So that has covered all the 10 operations, right? Then in the if block, we are doing our parallel computation. C of ID. So C stores the result of A and B. Okay, A of 0, then B of 0 plus, right? So we are going into the main program. So before moving forward, see, number of bytes to be allocated for n number of integers. So here we have taken n as a size, but we have to allocate the memory for that, right, in the bytes. So this is the variable where we can store the size of n numbers, okay? That size in the bytes is stored here. Then the steps we have already seen. So the first step is to allocate the memory on the host, that is on the CPU. How we can do that? By using this portion of the code. So we are taking pointers here, A, B, C, and we are allocating memory dynamically, right? So here A pointer, B pointer, and C we have allocated here, right? Then in the second step, we have to allocate the memory for the arrays DA, DB, DC on the device, right? So here we have taken some other variables that is used on GPU. So for that, how we can allocate that memory? By using the CUDA malloc. In C, we use the malloc for the dynamic memory allocation, and the CUDA, we can use CUDA malloc, okay? So this is the syntax, how we can do that. So here we have allocated memory on CUDA device. Then here we have initialized the values for the arrays, right? So randomly you can choose any values, but right now I am giving the whole array A value as a 1, and for B I am giving value as a 2, right? And the for loops starts from 0 to the less than n, that is size, right? And increments. Then the third step is to copy the data from CPU, that is from host to GPU, right? So this is the function to copy the data from host, that is from the CPU to the GPU. And how we can do that? By using this function. So here is the syntax. So here, this is the destination and this is the source, right? D of A is the destination that will goes on the device, and this is the host array, right? So the data of the A will be copied into the device memory, that is into the GPU memory, right? From A to DA. And how many number of bytes? That defined in the size. We have to mention it over here. And what is the direction of that? That is mentioned over here. CUDA mem copy host to device. So I have to copy the memory from the host to the device. That is from the CPU to the GPU. I have to copy the memory. Then again for the same, we are doing for B vector. So here is the source from host. We are going to transfer the memory to the DB. Okay. How many? Size. And same here, CUDA mem copy host to device. Same direction. Like from the host, we are going to transfer the memory to the GPU. Then here, we have to set the execution configuration parameters. So here, how many number of threads we have to assign and how many number of blocks we have to assign, we have to specify over here. So threads per block. So number of CUDA threads per block. How many I have to? So here you can consider a block. So how many number of threads we are going to use here and how many blocks per grid. So number of blocks in a grid. So how many blocks we are going to assign over here. Okay, that is in the variable blocks per grid. So here, threads per block. So I am taking 128 number of threads per block. Okay, not only 128 threads, 128 threads per block. In a block, I want 128 threads. The same we have seen here. In this block, I want 128 threads. Okay, then in the second one, 128 likewise. So how many blocks we have to assign over here? So this is the formula, right? So blocks per grid is equal to n plus threads per block minus 1. So n is the size, that is around 5120 into 1 lakh. Okay, that is the size we have taken plus thread per block. So we'll just take, suppose we take a 10 elements as thread per blocks, we will take 2, right? 10 plus 2, that is 12, minus 1, that is 11, and upon 2, 12 upon 2, that is 6. Okay. So n 51202 into, then threads per block 128 minus 1 and divided by threads per block. So it will accumulate all that threads into the blocks. Then we have to launch the kernel. So this is the next step. So here we are launching our kernel, that is we are telling GPU that do this task. Okay. So the function that we have to perform on the GPU, that this is the operation. The operation is written in the add vectors, right? Function. So here we have to mention how many blocks we are taking and how many threads per block we are taking over here. And these are the variables that we have used for the memory allocation on host. Okay. This is the kernel launch. Then here the operation is going to perform on GPU. So after successfully completing the tasks, we have to copy the data from GPU to CPU. So again, we copy the data from GPU to the CPU. So the same as whatever that we have done earlier, that we have copied the data from host to the device, right? So here we are copying the data from device to the host, right? So this is the source and this is the destination. So in DC, we have calculated the results and we are going to send it to C vector, right? This is the size and this is the direction. CUDA meme copy device to host. So this is the direction. So CUDA, please copy my memory from device to the host. So this direction I am giving. Okay. And this last block is to just confirm whether our results are right or not. Okay. We are just cross verifying that.
No, sir.
So if any value,
Akash, excuse me. Yeah, somebody had a question. Yeah.
Yeah.
Threads per block, the number of threads per block or in per grid you have written?
Number of threads in a block. Yeah. First, whenever we assign the number of blocks in a grid, so that is a blocks, number of blocks in a grid, right? So
Please go a little.
1 minute, just a minute.
It's written there number of threads per grid.
That's wrong. I have already told you. Okay. So here
Yes,
I'll
there,
edit
there.
here.
Number of
This is a block,
per grid.
right? I'll edit it later, right? So for a clear view, that is a grid. Suppose and you have a multiple blocks here. Suppose 1, 2, 3, 4. And in that, you have a multiple threads, right? These are blocks, and these are the threads. So threads in a block, okay, right? Understood? I hope your doubt is clear now. Okay, yeah.
How do you get the 128? Where did that come from?
128, right? Okay. So here you can change the size. So in the previous session, Bharat sir had told you can take a size 32 in the multiplies of 32, right? So here I have taken 128. You can take 256 accordingly. If you have multiple threads, like thousands, so here I have taken this much of size, right? 5120 into 1 lakh. So to accumulate that, I have taken 128. You can take 32 in that, right? 64, likewise. You can modify that as well, according to your use case, okay?
But it's not dependent on the architecture, or you can
No, that is
choose
not,
any-
like in CUDA or in any programming language, like you must, always you specify the number of threads in the multiplies of 32, 8 thread, 16 thread, likewise. And according to the architecture also, your numbering is the same, but the numbering goes, suppose there is a limit, like 1024 threads you can spawn per block or anything more. So that varies. But this is, you can change according to your use case.
Okay, thank you. I had one more question. Could you also explain the kernel launch syntax?
Kernel launch, okay. So here is the standard line that CUDA has given. So how actually it is going to be launched? So add vectors. What is add vectors? So here we have already mentioned add vectors, right? So this is our global function, add vectors. So these function I have to offload onto the GPU. So this operation, the operation written in the add vectors function, I have to execute on GPU. Okay, for that we have to tell GPU that this is my function. I have to offload it onto the GPU, right? And this is the size of blocks and blocks per grid, right? You have to mention. And then these are the device variables that we have earlier here. So int ABC, the pointers we have defined, that is the allocation on the GPU, right? That's it only. Understood? Okay. Yeah.
Hello, here. So when we see the specification of the device, it was there that 1024 thread per.
Right.
So it should not exceed 1024 or the.
No, you can't write down more than 1024.
Yeah,
Right.
it has to be less than.
Yeah, that's why I have told.
Is a physical limit something is there in the device or what?
Yeah.
Oh.
Okay, shall we move ahead? Okay.
So as previously mentioned, that a block will run in a SM, is that true or?
Right. That's also applied here. Right.
Okay, so then the number of threads you are deciding, is it motivated by the number of cores you have in a SM or something?
Yeah, you can do that. If you know the number of cores in the SM, you know well, then you can use that as well.
So ideally, will it not be the most efficient to use the number of threads per block to be same as that number of cores in a SM?
You can do that. If your application is like that, it using the thousands of the thread and you want more and more cores, you can do that. But the ideal 1024 is the limit for SM.
But then why not take 1024 here and go with a lower value?
Yeah, you can do that as well. You can try with that. What will happen with that? Okay.
Okay. Fine.
Okay.
Here is one more question.
Yeah.
So you are defining a number of blocks, right? So is it also constrained by number of cores, or what is the limit on how many blocks you can define?
So basically, there is no concern with the blocks as like the threads, because whenever you define the SMs having a specific amount of SMs we have on the GPU, right? So but how actually it runs? Suppose this is your GPU and you have SMs. Okay, 1, 2, 3 SMs, 4, 5, 6. Suppose you have a 6 SMs, right? So you have taken any numbers, like 128 number of threads you have taken, right? Okay. So accordingly, suppose you have assigned many threads, many thread blocks, right? So first block, second block, third block, parallelly it is assigned to any SM. Then after finishing this block, again second block comes and runs on that SM. Means second, then third, fourth, right? So suppose if any SM is idle right now, first task that it has done, then second moves on this SM. Like, so first execution done, suppose that is your GPU. So SM, so this is a block. So this is the SM. So this block finishes, then it is idle. Then again the next block which we have to perform. Okay, parallelly again same thing happen in multiple SMs.
Yeah, understood. Thanks.
Okay. Shall we move ahead? Okay. So here we have we are going to check the values whether it is right or not. So here you can see whatever the values that we have assigned for the A, that is 1, and for B we have taken the values all as a 2, right? And at the end, what we are doing? Freeing the memory. So for freeing the memory on the CPU, we have a free A, free B, free C, right? Then GPU memory. So we have CUDA free for DA, DB, DC, right? And then I just printed over here the number of blocks and size, whatever that we have taken. So I'll just compile this program. So type here nvcc -o. Then this code is compiled successfully. Then we are going to execute this code. So size is little bit more. So here, success. If our operation or not run properly, so it will throw this error, but right now we haven't seen any error. So the successfully we have completed, right? These number of size and thread per block and blocks in a grid we have taken over here. So just look it as a basic flow of CUDA program, right? So here we are not doing that much complex operations, right? So hope you understand this whole code, right? So shall we move ahead? Oh, yeah. Yeah, means what happens once you do any operation. So CPU also being utilized, just you're copying the memory, right? So the little bit operations are happening on CPU. Yeah, little bit utilization you can see 100 as well on CPU as well. Right, right. So next we'll see the matrix multiplication program. So first we will see the logic of the matrix multiplication, how actually it works. So I'll just show you one slide. I hope that you can able to see this GIF file. So you know how actually the matrix multiplication happens, right? So this is each element calculation is an independent task. Suppose we have to calculate the C11, right? So the first row and the first column, then second row, second column, likewise, right? So A11 into B11. So we'll start with the first row with the first column, A11 into B11, then plus A12 into B21, then plus A13 into B31, right? So the first row with the first column, we have done with that. So that is the result will be stored in C11, right? Then C12, the next one. So what is the resultant matrix should be looks like? So I hope that you know the basic rules, right? The number of rows in the first matrix and the number of columns in the second matrix should be the size of the resultant matrix, right? So what is the result for 1C12? That is A11 first row, then second column, then A11 into B12 plus A12 to B22 plus A13 into B32, right? Then for C21, that is second row, first column, and for C22, second row, second column. I hope that you already know about this, right? Do you have any doubt in this? So this is just a theoretical how mathematically we can calculate the matrix multiplication, right? So the same thing that we are going to do in CUDA. So first we will see how serially it is going to happen. That is a normal C program. Here we have declared one function, serial matrix multiplication. The elements that we are taking A, B, C and the result in C, right? H result. These are the input matrices HA, HB and H result, right? And this is the size that we are going to take. This is a 2D matrix. I think you have observed that. But see, whenever we use any kind of the 1D, 2Ds, so in the memory, it is going to be stored as like this. Suppose you have a 1D row that is A1, A2, A3, A4, A5, A6, A7, A8, A9. So this is going to be stored in the memory address M0, A1, M1, A2, M2, A3. So these kind of elements till A9, it is going to be stored in serial manner like this. Okay. A00, A01, 02, 10. So the second row is also going to be stored after first row, then third row. I know this CUDA is a little bit complicated language, but still, I'll just giving a brief idea about that, because in 3 hours, we can't learn CUDA properly, right? You have to give some time for that. So here, this is a normal C code for the matrix multiplication. Here we have allocated the memory. Okay. So we have taken the size for the matrix, 2D matrix, 128 into 128. Okay. N by N. So these are 3 variables. So here we have assigned array A, array B, array C, right? Then we have initialized the values. So for the matrix A, we are taking value as a 2. Then matrix B, we are taking value as a 3 for whole array. Then we are measuring the time, how much time it will take, right? And printing the information, how much time it has taken, and sample results, whether it is successfully computed, any result has gone or not. We will see with that. And later we will free in the memory. So basically this is the function, right? So I'll just explain this with a simple example, this logic. Okay, look here. Suppose I have 2 by 2 matrix, that is matrix A having element 1, 2, and 3, 4. Then matrix B having element 5, 6, 7, 8. Okay. So to find out the result, so first I have to calculate C00. Okay. So first we will take temporary value 0 as mentioned here in the code, TMP as a 0. Then we will calculate A into bracket I into N plus K. Here, suppose we have taken I as a 0, right? Then into N, the size, that is 2 plus K, right? Kth value is also 0. Then B, same. So that is the result is 5. Then again, we are taking A0 into 2 plus 1. Then same logic we are performing for 1, K of 1. Then result will be becomes 5 plus 27, that is a 19. Okay. So here C is computed as a 19. For the second C01, same logic is applied over here. So we don't have that much of time to explain it in deep. Okay. So just go through with that and add the result, you will get this matrix, right? So this matrix multiplication on CPU, you will get a lot of time to execute, right? So here I have taken a very small size, so it will take a small size, a small amount of time. But if I increase this, you we have copied the matrix flow from GPU. Then we have called the kernel and we have freeing the memory. Okay. This is -O. Okay, it is successfully compiled. And here I can able to see the executable. So here I'm mentioning how much time it is going to take. So here I have taken the size very long, that is 25,000. Let's see how much time it will take. So beforehand, we have decided to give you an access on Param series of supercomputers, but the users are huge. So for that, we haven't done that. So right now, I just give you a demo how we can run the same CUDA programs on HPC cluster. Okay. So if anybody from you having access of Rudra cluster, Param series of supercomputer, you can do the same process. Okay. I'll just give you a demo. So before logging onto the cluster, I'll just, so when you go into just type NSM infrastructure. So here on the infrastructure page, just wait a minute. The network is a little bit slower. I think the website is down right now. Okay. But still I have one PPT to show you. 1 minute. I hope that you can able to see my screen, right? So this is the architecture of Param supercomputers. Okay. So basically, here is the user. You can log in and you authenticate through the firewall. Then you first logged in on the login nodes. Okay, where you can compile your codes and do the file creation and all stuff you can do here. Okay. So this is the basic high performance computing architecture. Then whatever codes or the compute intensive task that you have to offload on CPU, whether it is on the GPU. So you have dedicated CPUs and GPU. So here you can see here 4 login nodes are there. Compute node, that is CPU only nodes are there. Then GPU compute nodes are there. So you can see here 10 number of GPU compute nodes are present over here, right? So I'm utilizing right now that nodes. So here I'm just logging onto the cluster. So this is my username. I hope that you can able to see, right? So this is my account username. Then paramrudra.iusc.res.in. This is the host name. Then port number. We have a port number 4422. Then we have to type CAPTCHA XNEXEAVH. Then I'll get a verification code on Google Authenticator. 496279. Then password. So here I have logged into my supercomputer. So here are some basic information how you can use the supercomputing cluster. So here I have some files. So the same console that we are using in Kaggle, but it is in the notebook, right? So the same commands like ls, we can list the files. Then I have one file named as test CUDA. Okay. So the VI is the editor. So this is the same program, matrix multiplication program I have wrote over here. Then in the Git, what you have copied earlier, you have the script. So in future, if you use any supercomputing cluster, then this is how you can run CUDA codes on that, right? Add script. So now I am on a login node, and if I want to move on the GPU node, so this is the script that I want to write. So basically, you cannot directly move on the GPU cluster. There are two ways you can interact with the compute nodes. That is, first one is the interactive, and the second one is the batch mode. So here I'm writing the script. So this is the batch mode. So why I'm writing the this script? Suppose you want to purchase some groceries, right? So first you will make the list, and then you give that list to the shopkeeper, right? Then he will give you the things that you have wrote in the list. So here I have written the job name, then where the output file is going to be stored, the CUDA.out, then error file, then which partition that I required. So I want GPU, right? So if you want CPU, then you have to mention over here CPU. And then how many, so on the Kaggle, we have seen T4 into 2. So 2 GPU cards was there. So here I want to use only 1 GPU card. So in our Rudra clusters, we also have 2 GPU cards on one node. So here I wanted to take only 1 card. Then I have made one reservation for this training purpose. So if you don't have any reservation, then your job will be in a queue state. Then how much time it will take to run. This is the approximate time, right? And then this is the package so NSM clusters provide some of the packages by pre-installed. So we have pre-installed CUDA package. Otherwise, if you have any system which doesn't have any CUDA setup and all, so you have to manually do that, then you can able to run the CUDA codes, right? So I'm going to compile this code on this login node. So module load CUDA 11.2. So if you don't do that, nvcc -version. So see, here command is not found. Like in Kaggle, they have already given the setup for the CUDA, right? So if I do the module load, CUDA, now nvcc -version, enter, okay? So here, now we are going to compile the code. The file name is test.cu. . I've logged out. Please note down this command because in future, if you are using any supercomputing cluster, these are the things that you keep in mind. So here, ICTS programs, then cat script.sh. Loading, then same command, nvcc, then I have one file test1.cu, then -o, executable name. So here it is successfully compiled. Then what I have to do to execute that file on the GPU compute node. So I have written the script. This is a slum script. Slum is a workload manager. In supercomputing cluster, we use workload managers to efficiently use the compute nodes. So to launch the job, to submit that job as batch, then we can see it. So this is the job ID, then the partition, what we have taken, right? This is a small job, so for that it has already finished, right? So there are two files has been generated. So one is the error file that we have written in the this much of time this operation has taken, and in the output file you can see some of the information about Param cluster. Okay, so we have taken very small matrix multiplication problem. So that's it. So till here, if you have any doubts, please let me know. So right now you don't have cluster access, I know, so I just given you the demo. So you can practice on Kaggle, but if you want something more, like you want to do the AI part, distributed training and all, so we are just giving the demo. You cannot able to do that on the Kaggle, okay? So if you have any doubts, then please let me know. I hope that CUDA is a very little bit complex language, right? So it will take time to understand, right? So daily practice this course and you can make your own as well. So this is just a demo because in 3 hours we can't finish the whole CUDA, right? We haven't taken some of the complex functions here as well. So do you have any doubts?
Yeah, anything for Akash to kind of discuss?
Thanks, Akash. So just to get an idea of us as a summary, we would be writing in C and then we are invoking CUDA in that.
Right.
And then that script has to be given as a bash script in Slurm to run in the cluster?
1 minute. I'll again explain that. Okay. So first thing, I have shown you the architecture, right? Right, this is the architecture of any supercomputer. It will always same, right? So see, first you are on a login node. When I have typed that command SSH, then username and my host name. So first it will landed on the login node, right? So on the login node, you can make directories, files, your regular operations you can do on that, right? But if your task is compute intensive, suppose like we have thousands of the users on each cluster. We have 18 plus supercomputers in the IITs and ISC and all, like in the research organizations, as you know. So for that, this is the standard architecture, right? So the slum is a resource manager, like login node is just to do the normal operations. But if you have some of the HPC applications like WRF and NWKM and all, so what you do that, you will make the installation and all on the login node, right? But whenever you want to compute all of stuff, then you have to offload it onto the compute nodes, right? So the offloading part we are going to do with the slum script. So the script is different. Suppose this is our application. You can consider test1 is our application. Suppose test1.cu is our application. And the setup and the code writing and all we have done on the login node, right? So for execution, so the actual operation when we want to do, then we have to do it on the compute nodes. So how the code will goes onto the compute node, right? So we cannot directly goes on the compute node. So there is one command sinfo. So here you can see the multiple number of nodes we have. Suppose there are 198 nodes are allocated. So node mean the standalone CPU, right? So standalone CPUs are arranged in such a way that like, have you seen any supercomputing cluster?
Not really, but I can appreciate this.
Okay. So there are number of nodes multiple, but how we can schedule that job, right? So for that scheduling, we have to use that slum script. So what actually it does, it will just take how many number of nodes that we want, how many cores that we want. We can just mention over it here. And the job is going to be offloaded on compute nodes. So right now we have taken it here GPU. So it goes on GPU, right? Is that clear?
Yeah, so that test1 is the CUDA executable which we were creating there.
Right.
So we just mentioned that here and it is just uploaded.
Right. Whatever the execution part, you have to mention over it here, right? After writing these things.
Okay, thank you.
Okay.